Where's my water? Oh, there it is. Can you pass me my water? Or actually, thank you. You want to try? There's a call. Try like the little.
Good afternoon, it's 12:30. Welcome to another Chem 401 lecture. When last we left our cast of characters, we were talking about entropy. And what I was attempting to convince you, successfully perhaps unsuccessfully, was that as matter was dispersed, entropy increases, and that is a more probable state. And we worked through this example, I believe. Did we work through this example last time? Any questions about that example? Are we convinced, or are we in process of being convinced? How many people are convinced about this entropy thing? Some of you. How many people are in process of being convinced? And how many people are unconvinced? That's fine. All right. Well, we'll keep talking about it. And now we'll go on to some more concrete examples. And for example, we'll talk about trends in entropy. And we'll actually start putting numbers to things. For example, trends in entropy. Entropy increases as you go from solid to liquid to gas state. And as an example, we can look at H2O liquid. Going to H2O gas. And I mentioned last time there were entropy values. They're tabulated on your conversion equation sheets. They are not delta S Fs or like delta H Fs. They are just S. They're the entropy. They are not changes because they're related to the fact that there is zero entropy at 0 Kelvin if it's perfectly liquid. The units, however, joules per mole Kelvin. And similar to delta HF values, you're going to look them up. And when you do, you will see that for liquid water, you get 69.9. And for H2O gas, you get 188.9. Yes. And yeah, so they get bigger. So what entropy is telling us is there is more entropy when you go from entropy increases when you go from liquid to gas. If we calculate delta S naught, there is the change. This is exactly like doing enthalpy delta H for delta H. It's going to be products minus reactants. And I get 118.9. Good. Entropy also increases as moles of gas increase. For this example, we're going to take dinitrogen tetroxide. Break it down into 2 moles of nitrogen dioxide. my entropy values, 304.2. 239.9, that is per mole. We are going to end up having 2 moles there of product. And very similar to how we would do this for delta H, coefficients do show up in this process. Products times coefficients minus reactants. The only small difference is all entropy values are positive. Sometimes delta HFs were positive, and sometimes they were negative. I didn't do these in my notes. Answer 175.6 joules per mole Kelvin. Next slide. Entropy increases as dissolved gases leave solution. What that means is you're dissolved in solution, dissolved gases, as they leave solution, they move from the aqueous phase to the gas phase. This time I'm not going to do the calculation. This time with all this space, I'm going to draw you a picture. I'm going to draw you a picture because that's one of the things I ask you to do on your homework number 5. And it says on your homework, draw a picture that makes clear how the product is more dispersed, because the product has a higher entropy. And our picture of gases, well, that's pretty straightforward. You take the particles and you place them very far apart, and you make little speed lines behind them to say that they're moving very fast. This particular time, I will actually draw the Lewis structure of my gas, because I'm going to draw the Lewis structure of my gas for my aqueous phase. Draw them relatively far apart and moving at high speeds. They are in the gas phase. Now for the aqueous phase, I'm going to again draw the Lewis structure. And I'll ask you to recall something from Chemistry 400 called the hydration shell of water molecules. When you think about the aqueous phase, what you think about is that whatever is dissolved in water, the partial positives and negatives are largely what makes things dissolve in water. It's a little more complicated than some of the things we did last semester, but we're still going to try it, and we're going to come up with at least a picture. We did this last semester for things like sodium ions and chloride ions that had clear 1 positive or 1 negative charges. I'm going to ask you to remember, so nitrogen in this molecule, is nitrogen going to be partially positive or partially negative? It's going to be partially negative. And at least for this picture, all we're going to do is when we draw the water molecule, we're going to draw the H part closer to it. And when we draw the water molecule around each of the H's, we're going to draw the O because hydrogen is partially positive. And we'll leave it at that. There is roughly a sphere around here. We can make it more complicated. What I'm going to now attempt to convince you is that this is more confined and therefore less dispersed than these, because entropy will increase as you go. And that's the kind, and in fact, that is exactly the picture that you can draw for your homework as well. Any questions about this picture? And if you ran the numbers similar to the last examples, you'd find the same. All right, now I'll go over for the general reaction how to calculate delta S naught reaction. For this particular one, it's going to be just like we did for delta H last semester. It's going to be the sum coefficients times the entropy value for each of the products over all products. Minus coefficients times the S naught values of our reactants. Then we'll do one more example. For me, like all thermodynamics calculations, the most important thing is to stay well organized. When I look up my values, I'll put them under each of the compounds, then do the math. So these are each of the values from the table. Now it's going to be products minus reactants. And in this particular case, I get 332.1. Joules per mole Kelvin. I guess technically, since this one only goes to the single digits place, 332. And that's it for entropy. We now understand entropy. It is crystal clear. Let's move on to the next topic. Well, as always, we'll have time, but we are moving on to the next topic. This is what's called the change in Gibbs free energy, delta G naught reaction. And a couple of things about the Gibbs free, what's called the Gibbs free energy. Gibbs, very famous physical chemist in the United States. Don't worry about it. We don't have to know names. All we have to know, and we don't even really have to know this, is the G for Gibbs and the G right there. That's where it comes from. If delta G naught reaction is negative, then the reaction is spontaneous. We've been talking before about trends in delta H. We said if a reaction is exothermic, it tends to be spontaneous. We said if entropy increases, it tends to be spontaneous. Delta G is going to put both of those trends together, and delta G says for sure whether something's spontaneous or not. One of the equations we'll see for delta G, the Gibbs free energy, or the change in Gibbs free energy, is that it's equal to the change in the enthalpy of reaction minus T times delta S naught reaction. And so if your question is how come delta G, the Gibbs free energy, or the change in Gibbs free energy, is the be-all, end-all of spontaneity, it's because it combines the other two trends. That's pretty much what it does. So to review, delta H less than 0 tends to be spontaneous. Delta S greater than 0, this means entropy is increasing, tends to be spontaneous. And when I say when delta G is negative, that is when delta H is less than 0, delta G is negative. With the minus sign here, when delta S is greater than 0, tends to make this negative, or does, it can make it. And therefore, delta G less than 0 is spontaneous. Now, we have a lot more to say about that, but that's what you need to know, and that's the reason we calculate delta G. Delta G will tell us whether a reaction will happen for sure. Let's talk for a minute about this temperature dependence term. I'm calling it T dependence for temperature dependence. For the temperature dependence, let's talk about the melting versus freezing of water. And I'll write out a reaction here. I guess I'll write it out for melting. So solid going to liquid. Freezing is just the opposite. This is a reaction that is oftentimes at equilibrium. My question for you is, at what temperatures does ice melt? Travis?
Anything above 0 degrees Celsius.
Anything above 0 degrees Celsius. So ice melts. Above 0 degrees Celsius. When does water freeze?
Below 0.
Below, yeah, thank you. So water freezes. Okay, so what I'm going to tell you is that this reaction is spontaneous in the forward direction above 0 degrees Celsius. So ice melts T greater than 0. Forward reaction is spontaneous at temperatures greater than 0. Water freezes. Reverse reaction is spontaneous at temperatures below 0. Are we comfortable with these statements? How many people are comfortable with those? How many people, so if you have any questions, now would be a great time. Okay. I'm going to make one more statement, and that is for if the reverse reaction is spontaneous, that means that the forward reaction is non-spontaneous. Meaning it doesn't happen. So the reaction can only be happening in one direction and not the other. We're now calling the direction that does not occur non-spontaneous.
Is
Yeah.
there a way we can think about this?
So I think your question, Anna, is if we only know delta H, can we tell if the reaction is spontaneous? And the short answer is no. We can tell what it tends to be. And so where we're going with this is from now on, we will do one of a couple things. One is we'll just straight out calculate delta G. If it's negative, reaction spontaneous, done. We could also, if be given enough information to do these two, and then use them to figure out delta G depending upon the temperature. Okay, so we're always going to be asking the question, is it spontaneous? And we're going to be giving you combinations of this to tell. Although it is true, if we don't give you enough information, you're going to have to tell us that. So if I said, it's an exothermic reaction, is it spontaneous? You would say, I don't know. It tends to be, but it depends on delta S. Right? So that's exactly where we're going, but in general, we will give you enough information and ask you if it's spontaneous. Another question? Kate?
So before reaction is spontaneous, it's not like reverse. Sorry. So before reaction is spontaneous, it's not like reverse reaction is not spontaneous.
Yes. So I did it for the reverse reaction. I did it for this case. But up here, for at t greater than 0, when the forward reaction is spontaneous, we can also say the reverse reaction is non-spontaneous. Yes. So is that your question, Kate?
Yeah.
There's always one direction that's spontaneous, and the reaction is happening, and there's always one direction that's not. And we've talked about this many times before, actually. If you remember, we talked about QC versus KC. And QC versus KC said, will the reaction happen in the forward direction? Will it happen in the reverse direction? The new word is, will the reaction happen in the forward direction spontaneously, or will it occur in the reverse direction spontaneously? But it's still the same. And we're getting to relating, like maybe today, maybe next lecture, relating delta G to those Q's and K's as well. So I don't know if that answers your question, but yes, at temperatures above 0 degrees Celsius, the reverse reaction is non-spontaneous. There's always one direction that's spontaneous and always one that's not. David, do you have a question?
Yeah, that pretty much answered it. My question was going to be, ice melting and water freezing, those are just controlled environments naturally. So if it was like a frozen lake, you would have to add energy to it, making it
So
non-spontaneous.
let's talk about the lake. The lake is always either freezing or melting. If the temperature is below 0 degrees Celsius, it's freezing. If it's above, it's melting. It may not look like it because it's such a big thing, but yeah, this applies to all systems. I mean, I guess the only time you could say that a lake is not freezing at below 0 degrees Celsius is if all of it froze, and it can't freeze anymore. So, but yeah, so it will keep trying to freeze. And, yeah. So I don't know if that answers your question. Any questions? There's actually one temperature we've omitted, because we've got greater than 0, we've got less than 0. What about 0? Well, do we know anything about 0 for this reaction between solid and liquid? Can we have solid at 0 degrees Celsius? Yes, we can. Can we have liquid at 0 degrees Celsius? Yes, we can. We did this whole thing in Chem 400 last semester for many of you, where we did what's called a heating curve. And if you remember, we said that as you heat, the temperature does not change, you just melt or freeze. At 0 degrees Celsius, both solid and liquid water are in equilibrium. And when delta G equals 0, the reaction is at equilibrium. Okay. I think I forget, oh yes. I'm getting ahead of myself. more about delta G. And I apologize, my delta went away at some point, but that's supposed to be a delta. Delta G equals 0. Reaction is at equilibrium. I think that's all I said. Yeah.
So which one's spontaneous?
Question, which one's spontaneous? Well, the reaction's at equilibrium, and meaning that that it's not changing. Yeah. So that's what it means. I mean, whenever things are at equilibrium, and I want to think about whether the reaction's happening, I actually want to think about QC versus KC a little bit more. But I'm hampered by the fact that this is a solid and this is a liquid in this example, so there is no way to get deeper in that way. And in fact, right, they're in equilibrium, so solid can turn into liquid, liquid can turn into solid, and they're just sort of skating back and forth. Anyway, let's talk about that more as we do more reactions. One more thing about delta Gn. We will only ever see delta G. We will never see G. That's the simplest way to think about that is since it's based on delta H, where there's only changes, there will only be changes in the free energy as well. So I guess what I want to write here is there are only changes in free energy. So delta G, you won't see any G's. Let's look at one more example. This is going to be for carbon as diamond. That's a solid form of carbon. Going to carbon graphite, if we look up the delta G values, and these will be delta G of formations, and now when you look at your conversion equation sheet, you will see that there are delta H Fs, delta G Fs, and S naught. So 3 columns, you are now able to use all of them. You'll look it up and you'll see that diamond is 2.9, graphite is 0. We calculate this in the same way that we do for delta H reaction. It's going to be, again, products minus reactants. I apologize, I didn't put my units right there. These are kilojoules per mole. And I end up with kilojoules per mole there. My question for you would then be, is the reaction turning diamond into graphite a spontaneous process? It is, and that is true. So, spontaneous forward. And our conclusion is that diamond will spontaneously form into graphite, or react to form graphite.
see compared, like, since this one's just 2.9, if it was like, say, 290,000, would it indicate that is a more spontaneous reaction, or do we just random the values?
Good question. Question was, so you know this is a slow process. How does that relate to this number being small? I would say two things to think about there. One thing is, as we talked about at the beginning, first figure out if a reaction is spontaneous. If it is, then you can think about the rate. When you think about the rate, in general, the most important thing is the activation energy. Although to some extent, the fact that this is a small number means that whatever the activation energy is, you're not getting much more stable when you go to the graphite. And so I would say in general, the thing to think about is the activation energy. But if we were to get more specific, if that was minus 290,000, what can happen is whatever the activation energy is, as soon as some of it goes to the product, there's enough energy to make more of it go. So, and the analogy would be something like charcoal turning into carbon dioxide. That's highly exothermic. Once you start that, it keeps going and it grills burgers. This one has both a high, very high activation energy, and it's not very, well, I would say the term is exergonic, but that means that it's not very much lowering the free energy. Does that answer your question? Yeah. Question, how about Nicole and then Rebecca? Yes.
What does delta GFF mean?
Oh, thank you. Delta GF is the change in free energy of formation. And that is completely analogous to the change in the enthalpy of formation. So, when I say they're completely analogous, I will say two more points about that. One is, you can use them in the same way that you use delta HFs. In Chem 400, how we used delta HFs was to find out whether reactions were exothermic or endothermic. Okay? And you can find out if they are, well, I guess the terms are, I don't know, the terms are endergonic and exergonic. I don't really use those terms in my class very much, so and you'll find them in the textbook. All I care about is that delta G is negative or positive. So, and the other thing is, so we talked a little bit last semester about delta HF and what the delta HF reaction was. And the same thing happens for delta GF. But what I've found is it's not helpful to talk about where it comes from, in the general sense. I'm happy to talk more about it, but I'm going to focus on using delta G. And I'll say a couple more words about that too. So in thermodynamics, there are, well, take a step back, literally and figuratively. Chemistry is like an onion. There are layers. And in thermodynamics, there are many layers. And the layers that I have chosen to go into, I went pretty deep into what is the meaning of entropy, because I think that's important and useful. I am not going very deep into some of the subtleties of delta G and delta GF. And I'm also not, if you read your textbook, going into some of the subtleties of the entropy of the surroundings. That's my choice. You either benefit or suffer from that choice because those are the things that are going to be on your exam. Hopefully you will find long term that those are good choices that I've made for you. We'll see. Anyway, so I'm happy to talk more about delta GF. We did a bunch with it last semester in Chem 400. And if there's any issues, please see me. Does that answer enough of your question, or for now, I guess? Yeah. It is, yeah, I think that's a good sum. For the deck. I know. I say that and everybody leaves. All right. So where were we? That's delta G. Delta G is the be-all, end-all of spontaneity. Delta G, so and again, we are focusing on these delta G values are always for the reactants and products. We're always focusing in this class on the reactants and products. We are, if something gives off free energy, because this is a negative number, if something is a spontaneous process, it is still giving off that free energy to the surroundings. In fact, let's see. We'll talk about more about free energy on the next page. Sorry, I was getting ahead of myself. All right. There we go. I want to do another calculation, or say a few more things about delta G. So the most important thing is, if the delta G for a reaction is negative, then the reaction is spontaneous. Now it's time to talk about that little not symbol there. It's not showed up in various aspects of this class. Okay, so this little symbol, it is the not symbol, so delta G reaction or not, or delta G not reaction. I think this is how you spell not. Certainly how I spell it. Not just means under standard conditions. And in thermodynamics, standard conditions means the following. Temperature equals 25 degrees Celsius. And that's really 25.000. That's like literally 25, not just 2 sig figs 25. Pressures are 1 bar. If you remember last semester, we said that 1 bar was approximately 0.98 atmospheres, so approximately equal to 1 atmosphere. And pretty much, we don't distinguish those two. Technically, it's 1 bar, though. But practically speaking, it's also 1 atmosphere as well. And when I say this, that means that to be at standard conditions, each gas must have a partial pressure of 1 bar. Square brackets, of course, mean concentration. Concentration of aqueous species is 1 molarity. Pure solids and liquids. And pure solids and liquids, that's related to the fact that solids and liquids don't show up in equilibrium constant expressions as well, because to be a solid or a liquid, the solvent, has got to be essentially pure. So that's all stuff that we've been doing. And I promise you, after talking a little bit about standard state, we won't talk much more about that either. But I just wanted to touch base with it. That's where the not comes from. And, okay. Now how to make it go away. I don't know if it'll go away. But here's what we're going to do with delta G. We're going to use the equation that I gave you And it's got all the knots on it, which makes you think that you're at standard state. And so far we are. If T is 298. Okay? But and I don't have a good way of doing this, so I'm just going to do it. If T is other than 298, I'm still going to use the knot. Even if T is, sorry, 25. I said 298, that's 298 Kelvin, that is 25 degrees Celsius. I'm sorry, all right, if it is not 25 degrees Celsius, still use knot. I hope that's okay. Again, another choice I'm making. Because then what's going to happen is we're going to take the knot away. And we're going to take the knot away, so no knot, not, if you will, is when we're not at partial pressures of 1 bar or 1 atmosphere, and we're not at concentrations of 1 molarity. And because we're doing 3 things. We are going to be totally standard. We are only going to have temperature be different than standard. And then all hell breaks loose. And nothing is standard, and there's no knot there. And that's sort of 3 ways to do it. In the past, I've played with having an asterisk here, but that didn't seem to work. It didn't seem. Anyway, that's where we are. So as we work over and through the calculations for the rest of the chapter, so come back to this if you have any questions about what's going on, what a delta G in particular means. Now, what is free energy? That's what I'm going to address next. We know that delta G, and the sign of delta G tells us whether a reaction is spontaneous or not. It's more than that. The free energy is the amount of energy available to do work. Actually, let me rephrase that. Free energy is the maximum amount of energy available to do work in a reversible process. And I'll say just a couple more, like that is like if and when on your second exam, there's a question that says, what is free energy? That will be the answer. I don't know if that's going to be on your second exam yet, but that is exactly what it is. Now let me say 2 other things. Well, this maximum amount of energy. Am I out of space? All right. Well, I'm gonna crawl up here then. This one's not gonna work either, but I'll pretend. Oh. If you remember last time, we talked about delta H, and we said delta H was the heat energy produced by a reaction. some of that energy is taken up in making things more dispersed. More disordered, if you will, but more dispersed. That's the entropy term. So, free energy is the maximum amount of energy available to do work. It is the maximum amount of energy once you've subtracted off the energy making gases expand and things like that. Okay? So if you were designing an engine, you would be interested in this amount of energy because that's the amount of energy you could, in theory, get out of it. So it's very engineering, which I like. That's the max, that's the amount of energy available to do work part. Now let's talk about this thing called a reversible process. A reversible process, and we actually touched on this last semester, though I never mentioned it. A reversible process would be if you were moving a piston by taking weights off of it. If you took the weights in 1 grain of sand increments off, that's about as slow as you can do it, right? The reversible process is the infinitely slow. And so have you ever driven a car? Some of you? Yeah. Do you know how the pistons work? Do those pistons go infinitely slowly? I hope not, because then your car goes infinitely slowly and it's not useful. But if you want to extract the maximum amount of work from any process, the process must go infinitely slowly. Anyway, finer points of what's going on, but the reversible process is a infinitely slow process. And so, it is not achievable, but it serves as a limit. It's sort of like math, when you have limits and you can't get to them, except in the real world. It's a limit that you can't get to. Anyway, so that's the definition. Like, what is free energy? That's why we have this thing beyond. Like, it does a lot more than tell us whether a reaction is spontaneous or not. But pretty much in Chem 401, that's a lot of what we use it for. Any questions about this? Marissa?
You can like redefine the reversible analogy as being
Yes.
If it's reversible, how is it?
Okay. An example, and these are my favorite examples. So I have 2 markers. I want to do a reversible process. And I want to therefore get the maximum amount of work out of it. So if I could do this, I would, but it would go like this. Right? And if this were somehow pulling something else, I could maximize the amount of work I could do by moving it as infinitely slowly, essentially. And it's true that you can actually see this move, so it's not infinitely slowly, but that's the idea, is you're doing it at the limit of how slow you can go. And if I just wanted to like pull a string not as efficiently, I would do what's called an irreversible process, and I would just go like that. I don't know if that clears up anything. Like reversible processes are infinitely slow. Irreversible processes are just faster. And you get less work out of them.
How did you relate that back to the piston with the car though?
Sure. Now let's go to the car. I think that's a better example. So in your cars, the pistons are going, I don't know, how many RPMs do cars go these days? 2,000, 3,000 RPMs, revolutions per minute. That means 2,000 to 3,000 times per minute that piston's going up and down. And it's not perfectly efficient, but it's efficient enough to drive. You get enough energy out of it to drive your car. If you wanted to maximize it, you would get, like, well, let's say this. If you were instead getting 50 revolutions per minute, you would be getting more work out of it, but you would be moving more slowly. I don't know, I don't know if, so Ethan, question, so.
You talked about last semester the size of the pistons playing a role.
Mhm.
Is that gonna help clear it up?
So, yes, like size, speed, basically the smaller the pistons and the slower the piston goes, the more closer to this reversible process you are. Question, how is more work being done if it's just being done more slowly? Here's what I'm going to do for you, and for everybody really, is I'm going to come, I don't have a good example, but I want to. I think it's a tangential yet interesting point to where we're going. And so how about I come up with an example that shows this? Because last semester what I did was I came up with an example for why smaller pistons in cars get you more energy, if for those of you who are there. And so I feel like there's an example out there. I just hadn't planned to do it today. So let me think about that. And I'll try and bring one on Monday. And either I'll either bring it to class or I'll have a handout that you can read. It's a very interesting point. It's very relevant for engineering. It's just not relevant to what's on our exams yet, though. But I'm open to having this part on exams too.
So if it moves infinitely slowly like it did, how does the ratio between potential energy and kinetic energy, how is that affected? So if it's moving that slowly, what does the potential energy be?
Okay. All right. So let me see. Thank you, David. Do you remember how things are path dependent? Something like work is path dependent, but delta S, delta H, and now delta G, they are state functions. They will not be path dependent. So it is related to the path that things are taking, and the faster. Yeah. Sorry. What was your question, David?
Oh, I was just asking, so like
slowly.
If it's moving that slowly, is its kinetic energy becoming less as potential energy ramping up?
So kinetic and potential energy, let's see. Potential energy is only related to position. Position is a state function as well. And so potential energy is also a state function.
Is it like analogous to like if you were to run a particular distance, you would get more energy, or if you were to walk a less energy to walk the same distance, or is that more related to distance than not running?
So it's definitely related to the path you're taking. I have to think about where it is. And I think you're on the right track with potential versus kinetic energy and the path that you take. I think, or I know, I just have to think about it more. Because I'm not sure, like the running versus walking thing does have different speeds, but then I'm not convinced about, like when I think about how energy is changing, that I know. So how about this? Can we put it in the parking lot for now? We'll come back to it. These are great questions. I really appreciate them. I'm sorry I can't answer them right now, but we will work on it. I will work on it. Yeah.
Last question on that.
I will not, so there are no penalties for asking questions in this class, so it will not be on the exam. Fair enough, right? Or, yeah, it won't be on the exam. I haven't written the exam yet. I am writing it between now and Monday, so I can have a practice exam also ready for you by Monday. And yes, this will definitely not be on the exam. I'm sure I've actually already been scheming as to what the last problem will be before now. So, and this was not.
Are you doing an answer sheet for the practice exam?
I am working on getting you an answer sheet for the practice exam as well. And I will let you know. How about this? I'm almost certain there will be one.
And if I can't get the answers, it's kind of.
Yeah, no, I get that. So the other thing I'll say is, even though I'm out of town, I'm at a conference, I will be available by email. The strange thing is, even though I'm at a conference, is I may be more available by email than I am sometimes when I'm teaching and in meetings. So, but,
You know who our subs will be?
so I know who most of your subs are going to be. So most of them is going to be Professor Alex Ischuk, who is very experienced. Professor Showa teaches.
Val.
I told you that.
So we are not taking request. We took one request. We searched. We could not get your one request. Anyway, it is more complicated than to find a sub than you might imagine, because lots of people teach at the same time as us.
Who's this Alex guy?
So if you have questions about who your subs are, please ask them after. But I am confident he is a very experienced Chem 401 instructor, and a good one, actually. Where were we? We still have plenty of time left, so we're going to keep going. This answer could be on your exam. The interpretation of it, probably not, or not. All right. My delta values, my deltas are still missing. But now we want to solve a typical bread and butter example. It says solve for delta H not reaction, delta S not reaction, and delta G not reaction for the dissolving of ammonium chloride solid, and analyze the results. The reaction I don't need my notes for, but the numbers I do. Dissolving reactions start with a solid. They go to aqueous species. In these cases, they will be ions. I will be needing my delta H, F values, knots, my S knots, and my delta G knots, and delta G formation knots. I'll write all my units over here, then I won't write my units as I work through the problem. Of course, I'll put my units back in at the end. And these values that I'm writing are all available to you. You will have all these values, and you will be expected to find some of them as you work through your exam. Speaking of your exam will be broken down into two parts that will give you more time to work on each part. One of them will be that Wednesday that your exam is scheduled for. Look for that to be about 100 to 110 of your points. Then 40 to 50 of them will be the following week in discussion. And I will have versions of each of those portions of the exam ready for you to practice. Question?
Are we ever going to have a quiz?
Are you ever going to have a quiz? Probably not.
So what are you going to do about that whole category?
Let's talk about that later.
Okay.
It is an issue that I'm aware of. Take all those down. All right. Now, so to calculate delta H naught reaction, delta S naught reaction, and delta G naught reaction, for this one with all 1 coefficients, it's all pretty straightforward. Take these two numbers, which are products, subtract off your reactant value. I'm just going to show the results so we can talk about the results. Delta H naught reaction. (14.0 kilojoules per mole). Is this reaction endothermic or exothermic? This reaction is endothermic. Endothermic reactions tend to not be spontaneous, not the whole story though. Now let's do delta S naught reaction. (73.2 joules per mole Kelvin). Does entropy decrease or increase? Entropy increases. That does tend to be spontaneous. And the question then is, what is delta G? Delta G in this case, delta G naught reaction minus 7.61. Kilojoules per mole. This reaction under standard conditions, 25 degrees Celsius, 1 molar concentrations, this reaction is spontaneous. This reaction is spontaneous under standard conditions. Question, Marissa? Question, will it ever happen where entropy increases and the reaction is not spontaneous? Yes. And there's a series of questions, one of which at least you'll see on your homework for this chapter, homework 5, that says, if the reaction is endothermic and the entropy increases, can it be spontaneous? And you would say yes. Can it be non-spontaneous? You can also say yes. It depends on the